Okay, so now we're going to dive into Bayes' theorem. And to get us ready for Bayes' theorem, we're going to have to go over something that we kind of tactically talked a little bit about when we mentioned a probability, and now we're going to do a full treatment of. And that's conditional probabilities. So before we were talking in terms of independent probabilities. If you roll one die, that doesn't affect the outcome of another die. They're independent. But conditional probabilities change based on an outcome. So it's sort of like if I roll a die and I roll an even number, so imagine a scenario where I roll a 4-sided die, and if it comes up even, then I roll an 8-sided die, and if it comes up odd, then I roll a 6-sided die. And I ask you, what are the chances on the second die roll that I get a 1? Well, that probability is a conditional probability. It changes based on some preceding event or some preceding condition. If I roll even here, then it's a 1 out of 8 chance that I get a 1. If I roll an odd here, then it's a 1 out of 6 chance I get a 1. So when in a tree diagram, when things are independent, then this part of the tree diagram is identical to this part of the tree diagram. Right? It doesn't change because it's not affected by some preceding part. But in a conditional probability, the parts of the tree diagram can change. Let's do just a really simplified example to show how this works. So let's imagine you're wondering, well, what are the chances that I'll have a job when I graduate? Well, that's conditional on a lot of things. Maybe it's conditional on grades, for example. If you get good grades, then your chance of getting a job is probably pretty good versus not getting it. If you get bad grades, then the chance of you getting a job is 40, or maybe is only 40, and 60% no jobs. I made up these numbers, by the way. Don't take this personally. Like the fact that I gave you only 30% chance of getting good grades and a 70% chance of getting bad grades. But just to simplify an example. So if you want to figure out the chance of you getting a no job, well, there's two different ways to get to a no job. But these probabilities are not constant because these probabilities are conditional on what happens here. Now we can figure out the likelihood of any one particular path because each one of these paths is mutually exclusive to the other, and because in the confines of that path, now these are independent, right? Because the only way to get from here to here, from here to here, is to get good grades. So that would be a 0.3 times a 0.8, a 0.3 times a 0.2, a 0.7 times a 0.4, a 0.7 times a 0.6. Now, again, I want to emphasize we are multiplying here even though they are not independent because we can, in the sense that we are multiplying different things. So if I were to ask you, well, what's the chance of getting good grades and no job? How do I want to put this? We can multiply here because we know all the conditions. So even though it's not independent, when we drill down this much, when we can map out all the different scenarios, then it is, for our purposes, independent. Right? It's a probability that is essentially constant within the confines of the tree diagram. So note here it's 20.24, 24%. Here it's 0.066%. And then, of course, you add those two together, you get 30%. 0.28, 0.42, add those two together, you get 70%. And then, of course, there's only two options here, 100%. Add all these up, 100%. So that's the basics of this. We can, of course, go even further. Because of these conditional probabilities, they can go all over the map. You can do all kinds of different things with them based on the scenario. For example, imagine someone who you could date. You could either date them or not date them. If you date them, There's a chance of a long relationship, maybe you get married, a chance of a medium relationship, you date for many years, a chance of a short relationship, you might only date for a couple months or less. But in order to get to any of these, you first have to have data in the first place. So these are obviously conditional on this, and this thing can just go nowhere. We attach probabilities to all these now 4 different scenarios. We could then apply a payoff to each one of these 4 different scenarios and multiply the chance of these 4 different scenarios by the corresponding payoff of the 4 different scenarios, add them all up, and then get expected value of this tree diagram, of this decision to try to date. So obviously this has little applications in business, because we can talk about maybe rather than date, it's a merger, for example, or to try some new product. The tricky part is figuring out the payoffs and figuring out the probabilities. That can be very hard, but even a rough estimate can be very useful in doing business decisions and just general life decisions. Bayes' theorem is a way to incorporate new information and update your expectations. It's a mathematical formula, which we'll be talking about in the next video, exactly what that formula looks like. But it's a mathematical formula that when you get new information, rather than saying, oh, well, this is definitely true or this is definitely not, you now know maybe how much more likely something is to be true. Like, for example, let's imagine you're testing people to see if they are taking drugs in your workplace. You might have this base understanding that maybe 1% of people take drugs just in your industry. So if you look at any random person, any random employee, you're like, well, you got a 1% chance. You don't know anything. But let's imagine this person tests positive for drugs. What should you conclude? Do you say, well, I go from a 1% to 100%? No, because it could have been a false positive, right? The test could be wrong. Similarly, this person tests negative. Does that mean you're like, well, you're definitely fine? 0% chance you're true. No, because the test could be wrong. It could be a false negative. Bayes' theorem is a way to tell you, now that you know this person tested positive for drugs, rather than being a 1% chance that there are drugs, maybe it's a 10% or a 20% or a 50% chance. Rather than this being a 1% chance this person is on drugs, now that they tested negative, maybe it's a 0.2% chance. In other words, it tells you how to incorporate the information. Obviously, these people don't have the same probability of being on drugs as they did before. Right? Obviously, you have new information. What do you do with that information? How much do you update your expectations? So Bayesian updating is typically the lingo that we use when we're talking about like how we change our expectations about the future when we get new information. And it comes from the equation I'll be showing you later. But for right now, we need to get some terminology and intuition down. So the 2 main terminologies are sensitivity and specificity. Specificity, say it with me. Specificity. Specificity. So sensitivity is the ability for the test in question to detect a positive state. And by the way, the test can be really anything, just any sort of rule that you're using. It doesn't have to be a literal drug test or a little test for disease. It could just be maybe some like method you're using to try to parse out what's going on based on imperfect information. So that basic idea happens a lot. So sensitivity is the ability to test a positive state. Positive state is whatever we're really testing for, essentially, whatever we're trying to seek out. Typically, it's whatever is unusual. So if we imagine 10 people who were using drugs walked in, and we tested all of them, and we only found out that 9 people, like the test only 9 people, right? Only 9 people came back positive. Well, that test is 90% sensitive. Right? It can correctly identify 90% of drug users, correctly identify 90% of the positive states. This other measure of accuracy is specificity, the ability to detect a negative state. So if we have 10 non-users walk into the room and we find out that, and the test does its thing and comes back at 8 non-users, so 8 negative results, then it's 80% specificity. Both of these are measures of accuracy. Sometimes you might see versions of Bayes' theorem where they just give one number for accuracy, and that's a simplified way to do it. But here you can see that sensitivity and specificity are very different things. One is the ability to detect a positive state. All these people use drugs. Is this person a terrorist? Is this person a good fit for this organization? Does this person have the disease? Whatever it is. And then the negative specificity, the ability to detect a negative state. So in practice, there's usually a trade-off between the two. If you want to make sure that you don't miss any positive states, make sure you hit it, then you are also more likely to incorrectly identify people as being part of the group, as being positive when they're really negative. Let me give you an extreme example of this. Just to sort of hopefully get the idea of the accuracy in our head. Let's imagine I want to have a party, and I don't want to have, let's imagine I want to have a party, and I only want to have certain kind of people there. And the kinds of people I want to have there are my fellow nerds. Right? I don't have any conversations about sports, but I want people asking what my favorite team is. I just want the conversations to be about nerdy things. And so to do so, I'm going to only get nerdy people to come. But my parties are really popular, and everybody wants to come, including people I don't want to be there. So I have to come up with some way to sort out the nerds from the non-nerds. And the way I come up with this is a question at the door. I'm going to ask people as they walk in, or as they try to walk in, the following question. If they get it right, I'm going to say, oh, you're a nerd, because only a nerd will get that right, and they get to come in. And if they don't get it right, a nerd would know that, and then make them leave. The question I'm going to ask them is, who is Luke Skywalker's father? Do you know the answer? That's right, it's Darth Vader. Now, do you think that all nerds will get that correct? Yeah, all nerds would get that correct. Right? Anyone who could possibly consider themselves to be a nerd will get that correct. Maybe there's like 1 or 2 random nerds that don't get it correct, but I think we can safely say that the sensitivity is 100%. But there's a problem with this question. Who will also get it correct? Non-nerds. Right? Virtually everyone knows this. There might be some people who are like, I don't know what I talk about, I don't know what to talk about. What? They won't know. But I think the vast majority of people who don't really consider themselves to be a nerd know even this bit of trivia. So my question for you is, what is the specificity? If you set a really high number, like 90, 95, or 100%, you have to be careful, because keep in mind, specificity is the ability to detect a negative state, the ability to correctly identify non-nerds in this case. And in this case, I got a lot of people who are non-nerds that got at my party. I said, who is Luke Skywalker's father? And a bunch of people with like their sports jerseys were like, it's Darth Vader. And I'm like, oh, you're such a nerd. And they go and they talk about, like, I don't know, the Falcons or some team I don't know about. Right? It doesn't work. Right? The specificity on this is actually really, really low. It has a very hard time detecting non-nerds. Like I said, there might be a couple people that don't know, but the specificity is probably like, I don't know, 1%. It doesn't do a good job. I could go even further. I'm like, I don't know, nerds are really good at math. So let's ask people what 2 plus 2 is. Well, the sensitivity is 100%, but the specificity is 0. Everyone knows what 2 plus 2 is. Right? In other words, all of my test results come back positive. Right? Everyone knows what it is. So I never miss a nerd, but I never correctly identify a non-nerd. So this is a bad question. Let's try a different question. So my question for the potential nerds to try to get in my party is, how did the crew of the Enterprise D beam the Moriarty hologram off the holodeck? How did they try to do that? Because of course a hologram on the holodeck can't enter the real world, unless of course it has the mobile emitter. It wasn't introduced until Voyager. It had a lot of potential. It didn't really make sense going through this uncharted part of the Delta Quadrant. It was like everything was like always in such really great shape. Battlestar Galactica was really great. Not the old version though, the new version. The new version is fantastic, but you should watch it. What was I saying? Oh, so how did they try to get Moriarty off the holodeck? The episode Ship in a Bottle? That's right. They decoupled the Heisenberg compensators. Duh. Now, did you know that? Oh, you a nerd? Ah. What do you think the specificity is? Think I correctly identified a lot of non-nerds? I think so too. I don't think anyone knows that. Probably very few people know that. I would suspect the specificity is 100%. The problem with this question is that it's pretty obscure. It's a bit of technobabble in Star Trek. Decouple the Heisenberg compensators. What does that even mean? So the specificity is high, but the sensitivity is pretty low. Right? Genuine nerds will not know that, and I will incorrectly identify them as non-nerds. I don't know, about 3% maybe? Decouple the Heisenberg compensators. It's not that hard to remember. So you can see this kind of a trade-off, right? If I make the question really easy, then yes, I have a very high sensitivity, but I have a very low specificity. If I make the question too hard, I get the reverse problem. The question is, how do you come up with a question that's just right? That's tricky. Right? This, by the way, is a lot of what governs my thinking when I write exam questions, what a lot of professors think about when they write exam questions. You want a question that isn't trivially hard, because you want to be able to identify, who doesn't actually know the material, but you don't want it so complicated that even people who know what's going on get lost. Right? It's a balance, and you kind of want a mix too. You want sort of a mix of of tricky questions and maybe a couple tricky ones and a couple of solid ones and a couple of easy ones. Because even if people can't get the easy ones, that tells you something. So that's a gradient there. Here we're just trying to get into a party. So it's tricky to come up with maybe a good question. Like maybe I could be saying who knows who is Luke Skywalker's father, but only accept Anakin Skywalker as an answer, because that's who it was. That's what he called himself when Luke Skywalker was conceived. So you could argue that's Force, the dark side of the Force, consumed him, and he's really a new person. Darth Vader is not actually Luke Skywalker's father. Anakin Skywalker is dead. You could argue that. So maybe I could do that, but that seems kind of a trick question. I don't know. I think a lot of non-nerds might not pick up on that. It's tricky to come up with a good question. And that's kind of the point. Right? No test is perfectly. No test has perfect sensitivity. No test has perfect specificity. They can get very high. As we'll find out, even seemingly accurate tests cannot be that helpful. Note that sensitivity and specificity are both conditional probabilities. What are the chances of a positive test result? Well, if they're a drug user, they're on drugs, then that's going to be a different possibility of a positive test result than if they're not on drugs. A positive test result is going to be one probability. If they're on drugs, it's going to be a different probability if they're not on drugs. So to do this, we need three pieces of information. Let's suppose 1% of people who work in our industry are drug users. Imagine 1% of our industry are drug users. We have a 90% sensitive test, so its sensitivity is 90%, and we have an 80% specific test. Specificity is 80%. To understand all the different possibilities, let's make a tree diagram. So I'm making it a little different. I'm going to make it this way because I have some flat lines that way. If they're a user, then the probability is, of course, 1%. If they're not a user, the probability of that is 1 minus this, 99%, or 0.99. Now, the test comes in. It can either be a positive or negative result both times. But just because the possibilities of the test result are the same does not mean the probabilities of the test results are the same. As mentioned, sensitivity and specificity are examples of conditional probabilities. If the user is a 1% chance, so assuming that they're a user, then that means we are looking at sensitivity, and the chance of a positive test result means the test result is correct. So we're going to go with 90%. If it is a negative test result, then that means the probability is not correct. That means the test result is not correct. If it's a negative test result, that means the result is not correct, and therefore we do 1 minus sensitivity to get that likelihood. And that's what you always want to be thinking about. Is the test result correct? Is it not correct? Which one is correct here, positive or negative? That's right, negative. Because they're not a user, then the correct result is the negative result. So that means we use specificity because we're working with not users, the negative state, and we'll make that 0.8 because it is correct. This is the positive result. This would be incorrect. Each of these outcomes have particular names. So if this is a user and we correctly identify them as a user in the test, then that test result is a true positive. If we do not correctly identify that user as a user, then that negative test result is a false negative. It's false because it is incorrect, and it's negative because it's a negative test result. If it is not a user, and we correctly identify them as not a user, then it is a true negative. And if they are not a user, but the test incorrectly thinks that they are, gives a positive result, then it is a false positive. So we have true positive, false negative, false positive, true negative. We can figure out the probability of each of these outcomes with just our simple mathematics that we've been doing with tree diagrams. What is the chance of someone being a user times the chance that they will be correctly identified as a user? So let's do that for all of them. So in this particular example, a 0.009 chance of a true positive, a 0.001 chance of a false negative, a 0.198 chance of a false positive, and a 0.792 chance of a true negative. So of course, if we add all these up, they get 1. If we add these two together, then we have a 1% chance, 0.01 for these drug users. If we add these two together, then we have a 99% chance, or 0.99 for the non-drug users. Now, here comes the interesting bit. Well, there's a couple of interesting bits. What's the chance of getting a positive result? Well, we can get a positive result in 2 different ways. We can get a positive result by traveling this way, or a positive result by going this way. There are 2 positive results. Just like when we're doing the construction example, there are multiple ways to get to 13 months and multiple ways to get to 12 months. So what are the chances of getting a positive result? What's going to be this plus this. It's the combine of these two things. So the chance of a positive test result is 0.207, or about 20.7% chance. About 20% chance, almost 21% chance that you'll get a positive result. Now, when you get a positive result, how should you interpret it? This is the Bayes theorem. When you get a positive result, how should you update your expectations for this person who got a positive result? Because you have to recognize that they might have got a positive result because they are actually on drugs, or they might have got a positive result because the test made a mistake. Well, what are the chances that the test is correct? Imagine that there's 1,000 people who took this test. Well, if there's 1,000 people that took the test, then that means that there are 9 people that have a true positive. And there are 198 people that have a false positive. So you take all 207 of them together. Pick one at random. What are the chances that you pick somebody that has a true test result, that has a true positive? Well, that would be, so what are the chances that the person is actually on drugs, assuming the test result is positive? Well, that would be all the true positives divided by all the positives, which is about 4.3%. Before testing, we thought that this random person had maybe a 1% chance of being a drug user. Now they've tested positive. Now there's a 4.3% chance. It is higher. They tested positive. We got more information. So it is higher than it was before. But it's not 100%. It's not even close. Appreciate how low that is. The person tested positive for drugs, but it's still very, very likely that they're not actually on drugs. And the reason why this is so different goes back to where we got that denominator from. Note, we got that denominator by taking our true positives and adding in our false positives. And the false positives is huge. The false positives completely overwhelm the true positives. Right? Most of that 0.207 is from the 0.198. And so even though the test seems like, oh, it's like 80% specific, it's like, well, 80% is really low. It's really low. It's not good at all. Especially when you're trying to test for something rare. Right? When you're trying to test for something rare, then most of the people that you're going to be encountering, most of the things you're going to be testing are things that are negative states. And so it's really important that your specificity is really, really high so that you don't get overwhelmed by false positives as you do in this example. Now in the notes, I might change this later, but in the notes right now, I've reversed the sensitivity and specificity. It's 80 for sensitivity and 90 for specificity. And when I do that and I make the specificity notably higher, then this number is not 4.3, it's more like almost 7.5%. That's a lot higher. That's still pretty low. Even 90% specific is still pretty low. It seems good, it's not. Not when you're testing for something that's very, very rare. The big takeaway here is it's hard to detect rare things. It just really is. Right? There's a lot of false positives. And Bayes' theorem teaches us that. It also teaches us, though, that we don't throw it away. We don't say, well, I guess it means nothing, right? Because we did go from 1 to 4. Right? They're 4 times as likely. But the point is they're only 4 times as likely. Now, even though I did Bayes' theorem here, you don't actually see the equation yet, and we're going to be doing the equation in the next video.